altering the hydrological cycle since the agricultural revolution, where cradles of civilization such as Mesopotamia and China were creating larger volumes of agricultural fields than any time previous. In doing so, one of the important technological advancements was the ability to move water from a place where there was surplus to where the crops were. This modification of the hydrological cycle meant that places and the ecosystem that required the water, where it was being diverted from, no longer had that water available to it. It also means that water which was not available previous can have a lot of different effects on the soil conditions in that area, but also the evapotranspiration rates in those areas. Usually in modern day society, we're moving water from more abundant climates where it's moisture rich to usually moisture deficit landscapes. One of the major water diversion areas in the United States is along the Colorado River, and we are diverting the water that is in existence in the Colorado River, which uninterrupted would flow into the Gulf of California, is now restructured and pulled into other locations such as the Central Arizona Project. And we know that Arizona is a very, very dry location. It's part of the Sonoran Desert. And when we put that water into this landscape, we're subjecting that water to higher rates of evaporation, which then is going to introduce more moisture into the atmosphere in those locations. That's going to drive all sorts of different changes in the hydrology of that system and across other states. Currently, with the alteration of hydrological cycle, we can undertake that change a couple of ways. The first one is to mine aquifers in modern day, and that's basically we're just drilling a well into the earth, and with a pump we're going to pull that water out and usually use it in situ. So we often consider this as mining the aquifer. The largest volume of water which has been mined out of aquifers goes to agricultural use. The Ogallala Aquifer, as illustrated in the diagrams on this slide, is delineated by a black oval. That aquifer is one of the largest in the world, and it has been around for a long time. The recharge rate of this aquifer is about 6,000 years. So for every volume of water which is mechanically removed with a well for agricultural or municipal use, it will take 6,000 years to replenish or return that water. So the extraction rate is much higher than the input rate, which then results in this aquifer diminishing over time. When we take a look at the state maps for which the Ogallala occupies, we see that they include South Dakota, Wyoming, Colorado, Kansas, New Mexico, Oklahoma, and Texas. All really important agricultural regions in the United States. And these areas have become far more fertile and economically productive for agriculture because of the Ogallala Aquifer. Since the time when we've been mining out water from the Ogallala, we find in that third map that is located on this slide that there are areas of huge deficit, namely Kansas, parts of Colorado, parts of Texas, Mexico, and Oklahoma are significantly withdrawn or lowered the volume of water in the Ogallala. This is going to impact the amount of agriculture that can be produced in those states, subsequently affecting the economic viability of agriculture in those states. It's going to change the lives of a lot of people in those states. And it's also going to change the foods that we eat here in the United States and the costs of those foods. So we've depended heavily on the Ogallala and aquifers like the Ogallala across the United States for base staples like food and driving stable economies. The second way that we have altered the hydrological cycle in modern day is simply to move water, as we said earlier, from one location to another location over land. We're capturing the water that is flowing through a river and not allowing it to empty out into its basin, into an ocean or a bay or a lake. We're going to dam that up. We're going to store that water in that dam and then slowly release that water across that river system and through canals that have been made to move that water into places that were dry. The illustration provided here is part of the Central Arizona Project with the irrigation districts delineated in the little black box in that top slide. The Yuma Irrigation District is a pullout of two satellite images. The one with the red and the cyan color is false infrared and is telling us the health and the density of the crops that are being produced in the Yuma Irrigation District because of the diversion of water out of the Colorado River and then into this now agriculturally relatively fertile location. Over time, however, when we put waters into an agricultural area that is really, really dry, what we found early in doing this activity is that there were poor management practices for water and soil at the time, and we've actually harmed the soil quite a bit through something called salinization. So a soil water budget then is how much water is coming into the soil versus how much water is leaving the soil. So a soil input is measured by how much precipitation there is. Is it falling as rain, snow, sleet, dew, and fog? All of that has the opportunity to penetrate and percolate into the soil below. The output rates are rates of evaporation out of that soil, rates of transpiration or evapotranspiration out of that soil through the plants themselves. The input and output rates are influenced by temperature and humidity, and each of those in the unique geographic location that the soil moisture budget is being measured in is going to then produce different characteristics of how much moisture is actually available for crop production. And that volume of water which is available is going to tell the agricultural community in that area what they should be able to plant with success. The soil water budget then is going to come down to, is there a deficit of water, which is essentially, is there enough water available as required for crop extraction and crop use? If there's not, under agricultural measurements is basically a function of a human-made condition, because in nature there is not a water deficit. The plants in the ecosystem are going to be able to adapt over time for those periods of low water availability in the soil. If we're talking long-term changes within the ecosystem where we've got serious droughts taking place for a series of decades or longer, then the ecosystems are going to shift and adjust to that. If we've got soil water budgets where we've got a surplus For agricultural purposes, again, we're speaking here, is that there is more water available than the plants can take up. That means that all the pore spaces within the soil are consumed, and we end up getting standing water on the surface of the crop or the field. This becomes really problematic because, just like drought, the plants aren't accustomed to that much water, and we're going to see crop failure as a result. With soil moisture storage, then, what is being recognized or measured is the accessibility of soil to the plants themselves. If you've got hygroscopic water, then we've got water which is bound to the soil particles. This is physically attached to soil particles. If you've got that much water or more, then there's enough water for the plants to be able to take that water up through capillary action and use that water from the soil. This is basically, there's enough water for the plants to use that soil. If the plants begin to wilt, what that's telling the agronomist or the farmer is that there's not enough water in the soil for the plant to maintain turgor pressure and stay erect. In that case, if the farmer is able to augment the soil moisture budget with irrigation, then the soil moisture then becomes hygroscopic and the plants are able to extract that water. If that farmer is not able to augment that water through irrigation, then the water isn't available at all and failure of that plant can start to take place. Field capacity is the amount of water that's available after the pores in the soil are drained. So we're really measuring how much physical space is between each particle of soil. That's going to be a cubic foot of potential water that gets stored in that rock structure. The capacity of a specific soil or geologic type is going to determine what the field capacity or the storage of water can be. And how much potentially stored water is going to tell the farmer again, how much water do I have for my plants over a given agricultural season. And he or she is going to be able to then to make some decisions on what they can plant based on what is actually in the aquifer or in the soil and in the geology versus what the field capacity could hold.